Welcome back to another episode of Dave Does Math from Home. This is part 3 of our video on section 16.5. We're doing triple integrals but round. In our first two videos we covered cylindrical coordinates, which are a lot like polar coordinates. It's polar coordinates and then you attach a z-axis to them. And we did some integrals with density, we did some integrals with space between two curves. I think it went pretty well. Now it's time to talk about spherical coordinates, which is a lot less like polar than you might expect. So to help me talk about spherical coordinates, I have constructed an axis, and I have a little B on the end of a Moltres, Articuno, and Zapdos pencil. So that's how serious I am about this. I wanted to use this to sort of demonstrate what spherical coordinates are doing. The pencil in this little cardboard thing is going to be the z-axis. We have the x-axis here, negative y goes down, negative x goes backwards, positive y goes up. So this is the xy plane that you already know and love. This is the z-axis coming out of it. Theta works exactly the same in spherical coordinates as it does in polar and cylindrical coordinates. Theta equals 0 is along the x-axis. As theta increases up to pi over 2, that gives you vertical. You can keep going. Theta goes all the way around this axis. 3 pi over 2 is straight down. This is theta. No surprises there. The weird part comes in when you want to leave the xy axis. You do so not by lifting yourself up or going straight down like a z-axis. You introduce a second angle. The second angle is called phi, and that rotates you up and down. So this is phi at 45 degrees, theta at 0 degrees. You can see it's right on the x-axis. That's your theta at 0 degrees. But vertically it's coming up. It's halfway in between the pencil z-axis and the cardboard xy plane. That's 45 degrees. Here's what's kind of weird about phi. Let me write some of this down. Spherical coordinates. In spherical coordinates we have theta, which is exactly what you think. Same as before. Phi looks like this. And I actually love these as like representations. Theta is the flat angle. It has the line going through it. Phi is the vertical angle. It has the line going vertically. This was cleverly done. Usually, I think most of you know that I really hate the way math things get named most of the time. I think most of these things were named by catastrophic idiots. But this one I like. Theta and phi I like, as the angle on the plane and the angle above the plane. So this is how it's spelled, this is how you write it. And here's what's a little weird about it. Phi equals 0 is vertical. Phi equals pi over 3, or pi over 6 is 30 degrees. That's 30 degrees off of the z-axis. 45 is right in the middle. 60 degrees is 60 degrees off of the z-axis, 30 degrees off the plane. Phi equals pi over 2. When phi hits 90 degrees, that's when it's on the xy plane. Phi equals, as you go higher than 90 degrees, you end up below the plane. Until you get to 180 degrees is straight down. And that's where phi ends. There's no sense in going past 180 degrees. That'll just put you, like if you go 270 degrees, you're back here on the negative x-axis. And like if you want to be on the negative x-axis, you should just go 90 degrees down on phi and then 180 degrees around on theta. That'll put you on the negative x-axis. Only one of these things needs to do the full 360. The other one only has to go 180. And if you go past 180, you can get to that same spot by going around on theta and then down on phi. Or if you want to talk about something like 315 degrees on phi, that's starting from here, going down, back down. This is 270 degrees. 315 would be here. This is 315 degrees on phi. And that's not how you would express that point. If you wanted to get to that point, you would go 45 degrees down on phi and 180 degrees around on theta. So that's what I mean when I say only one of these needs to do the full 360. The other one only needs to do a 180. So theta is the angle that gets to go 360, like by convention. Theta goes all the way around. Phi goes from 0 degrees is straight up along the z-axis, 90 degrees is on the xy plane, 180 degrees is straight down along the z-axis, and that's where it ends. If you want to go past it, you can accomplish that same position by editing theta instead. So that's our thing. Theta goes around this way, phi goes up and down on the z-axis, and then rho is how far this little b guy is along our pencil. So this is a small rho. This is a really tiny rho over here. You put him real close. This is a pretty big rho, way out by the eraser. This is a little b on the end of my pencil. It's very cute. So that's how spherical coordinates work. This is the vertical angle. It goes down from the positive z-axis. And rho, it's like a big scripty, looks like a P, spelled rho. This is the radius. This is how spherical coordinates work. And using spherical coordinates like this, it is really, really easy to generate things that are, you guessed it, spheres. If you want to see how much volume is in a tennis ball, you can kind of create, sorry, not how much volume. Tennis balls are mostly air on the inside. It's like a rubber shell filled with air. If you wanted to see how much rubber was in there, you could pretty easily create a description of a region that would model just the rubber in a tennis ball. So that would be something like, the region would be theta. It's going to go from 0 to 2 pi. And phi, no, that's not how we do it. Phi is going to go from 0 to pi, because we want theta going all the way around, and we only want phi going 180, because theta will take it the rest of the way around. And rho is going to go, how big is a tennis ball? Like, it's big. What's what? Like 9 centimeters across? Something like that. However big a tennis ball is, we could say that rho is going to go from, no, I guess if it's across that would be diameter, so I don't want radius. Let's go from 3.5 to 4. Theta going all the way around and phi going all the way down, this will generate the entire sphere. If rho only gets to go between 3.5 and 4, that means that we have a shell of a sphere. Like there's an outside sphere with a radius of 4, and there's an inside sphere with a radius of 3.5. And this is giving us all the volume between those two spheres without giving us the full filled inside of those spheres. It's just like the rubber shell of the tennis ball without all the air that's inside the tennis ball. So that's a cool thing we can do with spheres. Trying to model that region in rectangular or cylindrical coordinates would be a nightmare. Spherical coordinates gives us a lot of advantages if you're modeling things that are vaguely sphere-shaped, as you could imagine. I think one of my favorite things to model with spherical coordinates is like an ice cream cone. If you want to model something like this, doing this in spherical coordinates is really, really easy because you can just say, for this thing, let me erase this other thing. For this one, we can let theta go all the way around, 0 to 2 pi. We can let rho do the full 0, this is the origin, so we can let rho go the full thing from 0 to whatever this is. Let's say rho is 10. So rho can do the whole thing from 0 to 10. And the way you get this ice cream cone shape is you just limit phi. Phi is going to start at 0. Phi equals 0 is straight verticality. And you only want phi to go out to here. This line, maybe that's phi equals, what do you think, pi over 6? Pi over 4? Let's do pi over 6. Pi over 4 would be a bizarrely wide ice cream cone. So we'll do pi over 6. And bam, that's it, that's your ice cream cone. We can model this ice cream cone looking shape with nothing but constants in spherical coordinates, and that is key. We all know how easy these integrals become when you use exclusively constants as your bounds. Like trying to plug in functions as your bounds and these things, like it always kind of turns into a huge mess. So using nothing but constants is important, and we can get this goofy looking weird shape using nothing but constants in spherical coordinates, which is why I think spherical coordinates are really, really cool. I have no idea what I was going to say next. I completely lost my train of thought. Where were we going with this? Oh, yeah, so this is spherical coordinates. The point of this lesson isn't really to talk about what spherical coordinates are. The point is to talk about how to do triple integrals in spherical coordinates. So that's where we want to get to. And figuring out what spherical coordinates are and what they mean, that's a great first step. But it's not doing integrals, so we need to do integrals. Before we do integrals, we need to talk about some various conversions. So, hopefully, Everyone remembers the submarine problem from chapter 13. There's a problem that I put in the homework when we were first learning about vectors. It's about a submarine. It's giving you a submarine's speed, something like 30 knots or whatever, and it's telling you that it's moving southwest 30 degrees below the horizontal. And I love this problem so much because this problem is priming us for these things. 30 knots is our magnitude. 30 degrees below the horizontal is our phi. Technically that means that phi is 120 degrees because phi starts completely vertical. So the first 90 degrees will get you to the horizontal, and then to go 30 degrees below the horizontal, that's 120 degrees for phi. And theta going southwest, if we do y is north and x is east, then theta going southwest would be what is that? 225 degrees? I think that's 225 degrees on theta to go. Yeah, should be 225 to go southwest. And that is exactly how we can describe positions, locations, movement using spherical coordinates, and then sort of convert it into our rectangular coordinates. So the purpose of this question on that homework assignment was to sort of take this 30 knots, 30 degrees below horizontal, 45 degrees southwest information and sort of split that vector into all its different components. And hopefully that has primed us to talk about what x, oh, this marker, probably shouldn't have left it open while I waved and gesticulated about various things. Hopefully that problem has primed us to talk about what x and y and z are in spherical coordinates. And I want to talk about z first, because z is the one that sort of doesn't depend on theta. Theta will take us all the way around the xy axis. But it doesn't have anything to do with how tall we are. The only thing that has to do with how tall we are is phi and rho. So if we have this, if you have this angle phi coming off of the positive z-axis, that means that z, this z distance here, is the part that is adjacent to this angle phi. Which means that z should be rho times the cosine of phi. Cosine of phi will give us the vertical aspect of this. Rho will give us the magnitude. So z equals rho cosine phi. That's a good start. That means that this horizontal distance, I'm going to call it r for now. This horizontal distance is rho times the sine of phi. But that's not x or y. That's just the horizontal distance away from the z-axis. That's a radius. But we already know that x is r cosine theta and y is r sine theta. And if we know that r is rho sine phi, we can replace that here. Oh, this is not a good marker for erasing easily. Instead of r here, we're going to use rho times the sine of on both of these. So, I know this looks a mess, and it kind of is a mess, but we'll get used to it. X is rho sine of phi cosine theta, y is rho sine of phi sine theta, and z is just rho cosine phi. Write these down somewhere. They will be important later. And as always, we have x squared plus y squared plus z squared equals rho squared. This is the standard Pythagorean distance is the square root of the sum of the squares kind of situation. This is spherical coordinates. Next video starts with us doing integrals in spherical coordinates. Good luck.